Today we begin our study on rational functions. There's a few sections of this. So a rational function is just what it says it is. A ratio is a fraction. So a rational function is a function that's a fraction. To find the domain of a rational function, we have to take into account the bottom of the fraction because we know that we cannot divide by 0. So we take x minus 5 and set it equal to 0. And whatever we find there, 5 is not going to be part of the function. Now there's two options here, and you have to test for this. So it could be that there's a asymptote, a vertical asymptote at x equals 5, or it could be that there's a hole there. So the way we test to see if there's a hole or not is we take our function and we simplify it, we factor it as much as we can. Now that x squared minus 25 will factor to be x plus 5 times x minus 5. So you can see here that the x minus 5s would cancel out. Now that does not mean that x plus 5 is your function. Well, it kind of does. It would look like a line, yes. But this is still part of it. So what's going to happen is your line is going to look like this, but at x equals 5, there's going to be a hole. So it'll be like this deal. And so whatever that point is, 5 something, we could plug it in. I think it would be 10. Then you would have a hole there. If you have a case where it does not cancel out like this, then that's where we have an asymptote. So for example 2, let's look at this one. If we factor this one down, we've got x over x plus 5 times x minus 5, and nothing cancels out. So we're going to set our bottom equal to 0 and solve. And by the way, we didn't list our domain back here. It should be negative infinity to 5, and not including 5 because there's a hole there, unioned with 5 to infinity. Okay, back to example 2. Set both of these equal to 0. So something's happening at both x equals negative 5 and x equals 5. And since nothing canceled out in our function, that both of those are asymptotes. So when you graph this, you're going to end up with an asymptote at negative 5 and 5. And I'm not sure what the rest of your function would look like without going through the graphing, but we'll do that later. So your domain would be negative infinity to negative 5, and parenthesis at negative 5 because it's not included, unioned with negative 5 to 5, parentheses again, unioned with 5 to infinity. That's how we show in interval notation that we won't have it. If you're just doing regular notation, you would put something like this. And then this one, we can't factor on the bottom here. So nothing's going to cancel. And if we set the bottom equal to 0, we get x squared equals negative 25. So to solve this for x, to take the square root of both sides, then we will be taking the square root of a negative. And yes, we talked about how you could get irrational numbers, but in the case of domain, we don't worry about irrational numbers. So the fact is that there is nowhere in the real number system where this bottom would ever be 0. So that means our domain is all real numbers. Okay, arrow notation. We've already looked at this a little bit, but if it says x approaches a with a little plus up to the right, that means that x is approaching a from the right. If there's a little minus here, then x is approaching a, whatever the number a is, from the left. Then this one says if x approaches infinity and x approaches negative infinity. So we want to complete our sentences here. It says the graph of f of x equals x minus 1 over x minus 3 is given. Complete the statements. As x approaches infinity, f of x approaches what? So as x approaches infinity, that means as we move to the right, where are we going, up or down? It's going down, looks like, and stopping before we get to 1. So as x approaches infinity, or no, is that a... Yeah. So we're getting close to 1 there. As x approaches negative infinity, so as we move to the left, then we're also getting closer to 1, just from the bottom. But you don't have to put a little plus or minus there when you're going up and down. Then as x approaches 3 from the right, we're going up to infinity. And as x approaches 3 from the left, we're going down to negative infinity. A vertical asymptote is an asymptote that is vertical. And it is a spot where the graph is undefined. So we're getting closer and closer to the asymptote, but never touching it in both these cases here. Vertical asymptotes, the graph will never ever cross a vertical asymptote. It can cross a horizontal or slant, or sometimes we call slant an oblique asymptote. Slant and oblique would be the same thing, but we'll talk about those. Locating a vertical asymptote, basically like we just did when we found the domain. So here, to locate the vertical asymptote, we're going to start with simplifying. So if we can factor that bottom, we will. And we can, because negative 5 and 1 will multiply to give you negative 5 and add to give you negative 4. So if we set the bottom equal to 0, which means we'll set both of those equal to 0. No, if it gets dark, you're not going out. Then these are our two asymptotes. Now, when you're asked for an asymptote, a vertical asymptote, if you write 5, I'm going to count it wrong. And your online homework would count it wrong too. It is a line, a vertical line. And to list a vertical line, you say x equals 5 or x equals negative 1. So both of those are asymptotes in this case. Here we want to determine the behavior around the asymptotes. And I didn't include this one in your notes, but it doesn't hurt to go over it. It's basically the same as example 4. As x approaches infinity, we're getting closer to 0. As x approaches negative infinity, the purple graph there is getting closer to 0. As x approaches, let's start with negative 1. From the right, we're going up to infinity. As x approaches negative 1 from the left, we're going down to negative infinity. And as x approaches 5 from the right, we're going up to infinity. And as x approaches 5 from the left, we're going down to negative infinity. Example 6 says find the vertical asymptotes here. If we set x squared plus 25, the bottom, equal to 0, this is the same case where we end up with trying to take the square root of a negative number. So you can also see in the picture that there are no vertical asymptotes. A horizontal asymptote is an asymptote that's horizontal. You may have your graph approaching the horizontal asymptote and not crossing it, like in these two cases. Or you can see in this one, in this last picture, you're approaching the horizontal asymptote, but it does cross it over here. And that is okay with a horizontal asymptote. I'm sorry about him. He's just ornery today. Locating a horizontal asymptote. This is easier than it looks. Don't get scared. If n is less than m, what am I talking about? N is the top degree. M is the bottom degree. So if you've got your polynomial on top and your polynomial on bottom written all out, multiplied all out, with the highest degree first, and the degree on the top is less than the degree on the bottom, then the horizontal asymptote is always y equals 0. If the degree on the top is equal to the degree on the bottom, then the horizontal asymptote is a sub n over b sub n. What's that? That's the number in front of your x to the degree, both on the top and the bottom. So it's just the number on top and bottom. If n is greater than m, then there's no horizontal asymptote. So let's look at some examples. Find the horizontal asymptote of this graph. So here we see the degrees are equal. So the degree on the top equals the degree on the bottom. So in this case, then we pick the numbers out front, and those will be in our horizontal asymptote. So y equals 9 over 3, which of course can be simplified to y equals 3. So y equals 3 is your horizontal asymptote. Again, you have to have the y equals out front because it is a horizontal line. And here's a picture of it. You can see your horizontal asymptote going here. For this one, the degree on the top is 1, and the degree on the bottom is 2. So the degree on the top is less than the degree on the bottom. In that case, then your horizontal asymptote is y equals 0. And there you can see it. The last one, the degree on the top is 3, and the degree on the bottom is 2. So the degree on the top is greater than the degree on the bottom. When that happens, then that tells us that there is no horizontal asymptote. And here's a picture of that. This one actually will probably have a slant asymptote, but we'll look at that in the next video. Basic reciprocal functions. So this first one is, let's see, is an example of a rational function. And you can see here it is an odd function. If you plug in f of negative x, and we've covered odd and even functions and symmetry in previous sections. If you plug in negative x for x, you get negative f of x. Basically, if 1, 1 is 1, then negative 1 will be the other. That's the same thing, tells you that the symmetry is about the origin. For the second picture, it's an even function. If you plug in f of negative x, you get f of x. So 1, 1 would give you, or negative 1, 1 would give you back to 1, 1. And it has y-axis symmetry because it's symmetric about the y-axis. So use the graph of 1 over x to graph 1 over x plus 2 minus 1. Okay? So, first of all, the x plus 2 is telling us that we're moving left 2. And then the minus 1 is telling us that we're moving down 1. So every point will go left 2 and down 1. So if I start here, we move left 2 and down 1. If we start with this point, we move left 2 and down 1. It's useful to look at the asymptotes. So the vertical asymptote would be x equals 0. And if we move left 2, then the vertical asymptote is now at x equals negative 2. The horizontal asymptote would be y equals 0. So if we move down 1, then the horizontal asymptote is now at y equals negative 1. So this helps us with graphing. And we could always move some more points, but since they're not on perfect units, I'm not worrying about it. But it will look like that, the red one. And then lastly, we are going to start looking at what we call oblique or slant asymptotes. And that's when the asymptote is not horizontal or vertical. It's diagonal, either sloping up to the right or down to the right. To find an oblique asymptote, we have to do long division. So, we take the bottom and divide it into the top. So we've already looked at some examples of long division, but let's go through this. X squared goes into 3x cubed 3x times. Remember, if you're not sure about that, you can always go out to the side and do 3x cubed divided by x squared like this, and see that your 2 of the x's cancel out, so you're left with 3x. Then multiply back through. So 3x times x squared should give us 3x cubed. 3x times negative 9 gives us negative 27x. Then we subtract. So we change the signs. So we just get a 0 there and end up with a 27x there. There's nothing else to bring down in here, so we don't have to worry about that. We're done. Your answer, we don't even care about the remainder. It's just what's on top. So the slant asymptote would be y equals 3x. And hopefully I've got a picture here for you to look at. So you can see, here's the purple is your graph, and your slant asymptote, y equals 3x, is graphed dashed there. Yes, the graph will cross it, and that's okay, but then you can see where up here it's getting close to it and not crossing it, and down there it's getting close and not crossing it. So that concludes our first video on rational functions. We'll pick it up shortly.